Hello everyone. We have reached the prediction portion of this course, and with that we're going to go to chapter 13. The title of the chapter is Linear Regression and Correlation, perhaps one of the most powerful techniques in statistics, regression analysis, which is used in order to make predictions. So here the idea is to predict the value of one variable from the knowledge of another variable. The idea of linear regression, of course, is a very basic idea in this chapter for us. It's a topic that reaches far beyond what we're talking about. With this, with the regression analysis, in fact, we can go into many dimensions, and we can actually expand everything that we're doing in this chapter to multiple independent variables. So before we actually look at how the regression analysis and correlation works, I'd like to do a little brief review of algebra with you. Most of you probably remember this. Some of you may not, because it's been a while you've had algebra classes, but I'm sure it will come back to you. Keep in mind, we're going to use Megastat. That means we're going to use software in order to do the analysis, regression analysis and correlation. That is, we're not going to see any of the formulas at all. In fact, we're just going to go right to the output when it's time to do so. Also, just to forewarn you, the outputs that you're about to see, the initial outputs, they're not from Megastat. So don't be alarmed by that. It's like, well, we're not using the software you're using, we are using Megastat. How do we do it in Megastat? I will show you in Megastat how to do things, but I just want you to focus on the ideas of the chapter and the topics that we cover. And when it's time, near the very end of this lecture, I'm going to go to Megastat and actually run everything that you see in bits and pieces. You will see in one run of Megastat. So we're going to save the best for last. Best being the work in Megastat. So let's begin by a review of equations of a line. If you recall from probably algebra classes, this is the equation of a line. Okay, what I have here, y equal mx plus b. And in this form, m is the slope of the line and b is the y component of the y-intercept. And the variable x is called independent variable, and the variable y is called dependent variable. Okay, that's what those two things are. And if you recall the interpretation of a slope, the slope, most people call it rise over run, but as I mentioned, that here I have written, that's pretty generic definition. It's okay for now to think of it as that. A more formal definition of that is the change in y over the change in x as you go from one point to the next point on the line. And here's what we mean as far as going from one point to the next point. So suppose here, I'm going to make a drawing and then I'm going to erase this. Here's a line. Let's say I have a point here and I have a point here. The change in y, well, this is a change in y as I go from, I'm going to go from lower point to higher point, so I'm going to go in that direction. So this would be the change in y, a positive change, and this much would be the change in x, a positive change in x also. Or you can go to the right, that's the change in x, change in y, either way you go with. So that's what the definition, the formal definition is. So the ratio of those two numbers give you the slope of a line. Now, if you recall, the slope of a line tends to quantify the slant or the steepness of a line. How steep is this line? So it tends to quantify it, put it in terms of numbers. The steeper the line, the greater the slope. Now, here I have three scenarios. This one is a case where the slope of a line is 0. So notice how the line is, we call flatlining. It's a horizontal line. Now, in case of a horizontal line, let's say I go from this point to this point, and it doesn't make a difference, by the way, whether I go from left to right or if I go from right to left. Either way I do this. There is in fact a change in x. As you can see, that much is a change in x, but there is no change in y. Okay, because there is no change in y, so the change in y is 0. That's the numerator of the slope, as it is in here. Change in y. And that would be the rise, in other words. There is no rise as I go from left point to the right point. And the distance from left to right, call that x. There you go. And 0 over any non-zero number is 0. So that's why the slope of this line is 0. Therefore, a line that's flatlining has a slope 0. Okay, oops. I didn't want to get rid of the vertical axis here, but that's okay. Okay, and oops, that completely got rid of it. Let me put it back on. Okay, so I went ahead and put that line back in there. So anyway, that would be the slope 0. That means a horizontal line. If a line has positive slope, there you go, this would be the orientation of this line. The line is, it's going to rise from here, from left to right, as it goes from lower left to the upper right. Okay, it's going to go in this direction. Here's the lower left, here's the upper right. So that's going to be the line that has positive slope. A line that has negative slope, notice how it's falling in this direction. It's actually going down. You go from top left to bottom right. So that's going to be the orientation of the line. It's going to be like this. Okay. Now, the equation of this line in statistics actually going to take on a slightly different form for us. Okay. So the form that we're going to look at is actually this form right in here. See, instead of b up here, which is the y-intercept, we have b sub 0. And in turn, instead of m, the slope of the line, m times x, we're going to have b sub 1 times x. And the reason it's done this way is because if we were to do multiple regression, in multiple regression, the more x's we have, like this in multiple regression, this becomes x1, x2, x3, x4, x5, and so on. And then we can continue the pattern with the b's. So the b's become b1, b2, b3, b4. So it just lends itself better for multiple regression. That's why they change it from mx plus b to b sub 0 plus b sub 1x. So in this form, again, b sub 0, right in here, this is going to be the number. Here is going to be the y-intercept. And b sub 1, the coefficient on x, is going to be the slope of a line. Okay? And that's what that is. So, now, that's all the review we needed for lines. So, down here now, I have actually the objective. What are we trying to do in this chapter? Very simple. We would like to again be able to predict the value of one variable, which we call dependent variable, from the knowledge of another variable. And that's going to be independent variable. Now, as far as the data is concerned, our data is going to be what we say, or what we call a bivariate data, meaning there are two variables. Okay, right here. We have two variables, x comma y. So, xy, either one, of course, could be quantitative or qualitative. We have a means of handling these. But in our work in this course, primarily both variables are going to be quantitative variables. Okay, so we're going to assume both variables are quantitative. Now, the other assumption is that our independent variable, which is x, is assumed to be fixed or non-random and measured without error. And dependent variable is assumed to be random. Okay, so that's going to be our assumption. So the only random variable here is going to be y, but x's will be fixed. And I'll clarify that in a few minutes. Now, some of the terminologies that we use with independent and dependent variables are: independent variables are also known or called explanatory, predictor, and regressor, while dependent variables are known as response, predicted, and regressed. So those who go with regressor on the independent, those folks call dependent variable regressed. Those who call the x predictor, they call the y predicted. Okay, so let me add this in here, that's going to be your x, and this is going to be your y variable. Okay. Now, just a little historical note here. The gentleman who's responsible for actually initiating this whole idea of regression analysis is Sir Francis Galton. And Mr. Galton came with the idea of regression in actually one of the projects, one of the problems he was working. He was interested in trying to predict. Actually, he was looking into the correlation or relationship between the heights of sons and fathers. And his theory or his premise was that the taller the taller the father, the taller the height the son would be. So the taller the son, the height of the son would be taller also. For taller fathers, they have taller sons. And that was true. In fact, his data showed that until a point where as the height of the father grew, the height of the son didn't grow as much. So the height of the son tend to regress or go back toward the center, the average height for the data set. And that's where he came with the term regression. It means going back. Remember, progression is going forward, regress to go backward. So the term regression is to go back toward the mean. That's where he coined the term regression analysis, or just regression, and from that came regression analysis. So here's the idea of regression. This is what we call a scatter plot. Okay, so this is what the scatter plot is right in here. So what is a scatter plot? A scatter plot is a two-dimensional plot of y versus x, just like in algebra classes. So because we have bivariate data, each of these dots that I have here, each of these represent a pair of data. So the idea is to fit a line through these data points for this data set made up there. Now there are several ways we can draw the line. For example, I can maybe draw a prediction line like this. Of course, you can see visually that that line is a poor fit. True. Or I can say, let's say my line may look like that. That is also a poor fit. So there are several ways we can draw. There you go. These are all possible lines. Don't worry. I know visually distracting, but I'm going to erase all of these. There you go. And that's the idea of regression. So what if I want to draw a line that makes the best prediction among all of these lines? Now, of course, the colored line I have is the best line of fit because it kind of goes through in such a way that it looks like it's close. It goes right through this bunch of the data points. Now, the rest of these lines are poor lines, so I'm just going to remove these. Okay. And this is going to be the line of best fit. So our objective in chapter 13 is to find the equation of this line, which again, Megastat or any software will find it for us. Okay. Now, what is the criterion we're going to use for the line of best fit? So I have it here in this line. So let's agree that the line of best fit is going to be the one that gets as close as possible to every point in the scatter diagram. Now, because we're looking for one continuous, one segment of a line, a straight line that should be. So zigzags like this is not allowed. Okay, that's not going to be a line, as you can see. So we're looking at one piece, one line that goes through these data points, in fact. Okay. Now, and mathematically speaking, this is what we want to do ideally. We would like to minimize the vertical distances between the fitted line and observed value of y. Okay, and this line, the line that characterizes like this as such, is called the regression line. Now, this idea of minimizing the vertical distances, as I have here, minimize vertical distances from the fitted line, means this. So down here, I have created this hypothetical chart again, to where I have, there you go, this is the actual observed value for a pair of data points x, y. So that's the observed value, the actual value. And then in green, this green box here, this is, let's say, the predicted value by the regression line. So we're going to say the best line of fit is the one that minimizes this vertical distance between the two of them. Okay, and we're talking about this distance right here. So that distance, the difference between the observed and predicted value, is what we call the residual or error. Okay, and that's E. The subscript I have here is because, let's say I have a sample size 10. So I'm looking at, let's say, the 5th observation. So the subscript I means the ith. I'm looking at the ith observation. So it could be 1st, 2nd, 3rd, 5th, whatever. It's just one data point in our data set. So the error or residual is going to be the difference between y sub I is the actual value and minus the predicted value. Notice predicted value also y sub I, only with a hat or a caret sign on it. So there you have. The mathematical engine behind what we're doing is based on what we call least squares criterion, therefore. And what is least square criterion? Least square criterion says the line that best fits the points having the smallest possible sum of a squared of errors. Because remember, the error that you see here, this error is only for one pair of observations. So let's say if I have a data set with 20 data points, I'm going to have 20 of these individual residuals. So we're going to square each of these residuals or errors and then add them up. And that's how we get sum, means add them up. Squared errors, that's the square of residuals. And we'll see notationally in a moment how we write that mathematically, symbolically. So that's going to be our criterion. Okay, and there you go. Now, the reason we actually, why do we look at sum of squared? So what's the deal about squaring them? Why don't we just sum them instead of squaring them? Just add up all those residuals. Well, interestingly, it turns out that if you add the individual residuals for all data points, those individual data points will add to 0. Interesting. So no matter how you make up these numbers, you fit a regression line through them, the sum of residuals or errors is going to be 0. That's before you square them. Now, you can think of that part of the reason being because some of these errors are positive, some of those are negative. If the observed value sits above, like let's say for example, again going back up here, if observed value sits above predicted value, when you subtract the higher the number on top from the number on the bottom, the higher number from lower number, we're going to get a positive residual. So a positive residual, that means the point actually sits above the regression line. Okay, so in my drawing here, this is going to be a positive residual. This is going to be negative residual. So as you can see, some of these are positive, some of these will be negative, right? Residuals. Now, if you add up all of these positive and negative residuals, they're going to add up to 0. So that is the reason we have to actually square them. Okay, because the squaring them will turn positive, negative, doesn't matter. Either way, it turns into a positive. Okay, that's just the reason for squaring them. So, now the model for what we're doing, the population regression line is going to look like these. Okay, and in our work, by the way, the kind of regression analysis we're doing is called simple linear or first order regression model. First order regression model. Now, a first order regression model means you have only one independent variable. Okay, and first order means x is to the first degree. Okay, the order of the model is the degree on independent variable x. And notice the B's that we had before. Remember this one was like B sub 0. This was B sub 1. Because we use those for the sample. We're looking at population model here. See? This is the population model. So in the population, the B's turn out into betas. Okay? And that's what the population model is. And this is like if you fit, let's say I have 200 million FICO scores and the person's age. Okay, and if I want to fit a regression through those where I can predict the FICO score of a 35-year-old, this is going to be the model. This is the model in green that I have. This model is the model for every possible pair in the population, which we don't have. We're going to use a sample. The sample regression model I have directly below it. There we go. This is the sample regression model. So y becomes y hat, beta 0 becomes b sub 0, beta 1 becomes b sub 1. Okay. And the y hat, of course, is a predicted value. Okay. Now, just a note here as far as like what is it that we are predicting. Okay, so what we're predicting indeed is what we call the expected value or average value of y for a given level of x. Symbolically, that's what we're doing. So for example, when I predict the FICO score of a 30-year-old, we got millions of 30-year-olds, right? So what am I predicting? Which one of them? Well, we're predicting the FICO scores of an average 30-year-old. Okay, the average person. So that's what we're predicting. Now, just the terminology here again. So we have a couple of definitions here, or terminologies. What is a regression line? The line that best fits a set of data points according to least squares criterion. We mentioned that up earlier. And the regression equation is the equation of that regression line. The line of best fit is called the regression equation. Now, couple of ideas here. So in this data set, and don't worry about what the data is, but if you're curious here, the age in years, these are the age of some automobiles, and these are the prices of them. Okay, these automobiles are let's say these are Orions. Okay, or this could be whatever automobile that, for example, a 1 year old. Well, I don't have any number for 1 year old. See, there's no data up here that goes with it. Nothing here. So it looks like 2-year-old is the youngest model here, and that's the price, which is roughly the price is about $17,000. So that's what these are, in case you wondered what they are. Okay. And for instance, the price of a 7-year-old of this model, of this automobile, we got 2 7-year-olds. These are the prices. One of them looks to be about almost between $4,000 to $5,000. The other one is about $7,000 roughly. So that's what these are. But that's beside the point. What I want to mention or talk about here is a couple of interesting ideas, and those are influential and observational. Influential observations and outliers. Now, so here in this drawing you have 2 regression lines. Okay, this point is called an influential observation. Influential observations are those points that lie along the influentials. I have them here. They lie alongside the regression equation. Okay, that's what they are. So for example, look at the blue line here. I'm going to draw a dot right down here in below, lower right corner, right in here. That's going to be an influential observation. So they're far away from the rest, but they are, there you go. They're still alongside the regression line. So these are called influential observation. And what exactly they influence? They influence the slope of the regression line. So in this other drawing, see, this influential observation is removed, and look at how the slope of the line changed. The slant of the line changed. Right? This is removed. Now, this is a new line. Removing this single observation from data. So that single observation is really influencing the slope of the regression. The other idea is outliers. Now, outliers are those that are away. They are away from the trend line. So, looking at the chart that's up here, I don't see any. I'm looking at the blue line. I don't see any outliers. What would an outlier look like up there? So, for example, look at the 7-year-old. Okay, I'm down here. I'm up here. That's for the card. That's 7 years old. If I had an observation whose y value was there, that would be an outlier. See how it sits away from the blue line? These two lines, not two lines, these two data points are near the blue line. But this one is far away from it. Okay, so that would be an outlier. Okay. And that's what I'm trying to show you in my drawing here. So I have a whole bunch of data. Here's the regression line. And I have this point that sits apart from the rest of them. So let's say here, there you go. That would be at x sub 1, and this would be at this level of x sub 2. So the points, these points, and let me just draw a line. There you go. All of these points pretty much are bunched together, and then all of a sudden you have this one that's away from the rest at x sub 2 at that level of x. Okay. Now, that's all we want to talk about. So how do we find the equation of this regression line? Let's take a look at an example. So you're about to see computer outputs here, okay? But these are not from Megastat. These are bits and pieces again. So we're going to go through and talk about regression and correlation. And again, it's in the very end, near the end of this video, that we'll look at how to run this in Megastat. Okay, so here's our example. Let's say we have custom homes. Hana Properties specializes in custom resales in equestrian estates and exclusive subdivision in Phoenix, Arizona. A random sample of 9 custom homes currently listed for sale provided the following information on size and price. Here, X denotes in hundreds of square feet, rounded to the nearest hundred, and Y denotes the price. So X is size, Y is the price in thousands of dollars. Okay, to round to the nearest thousand. And we want to predict from this data, we want to predict the price of 2,600 square feet home in that state. You can kind of see the raw data here. So for example, let's look at in the middle here, 34. X is the size in hundreds of square feet. So 34 means that 3,400 square feet. A 3,400 square feet home in that estate sells for $661,000. Okay, so that's what that is. And so what are the X and Y? Well, X in this case is the size of the house in square feet, let's say hundreds of square feet according to this data, and the price is in thousands. Okay, so that's what those are. Our independent variable is size. Our predicted or response variable is Y. What's being predicted is the price. Okay, as far as how do we decide which is dependent, which is independent, well, think about it. It is the size of the house which determines the price, right? And I know it's all about location, but let's say we're looking at a cul-de-sac. We're in that zip code and literally on the same city block. And on the same side of the street, everything being the same in a cul-de-sac. So if I'm looking at a cul-de-sac and I'm looking at homes that are very similar here. So it wouldn't make sense if you want to predict the size of a house from the price, but it would make sense to predict the price of a house based on the size, because size determines the price. not the other way around, right? For example, if my house is worth $1 million, it doesn't mean that it's necessarily 5,000 square feet. But in the same cul-de-sac, if I look at the 5,000 square feet home, I can determine the price, 4,000, probably going to be lower than 5,000 square feet. 2,000 is going to be lower than 4,000 square feet. So that's how you determine which variable is which. So in regression, of course, it makes a difference which is dependent, which is independent variable. But in correlation analysis, sometimes it doesn't make a difference which is x, which is y. That's just in correlation. That means if you just want to measure the association between two variables, assuming that they're both random, of course, it doesn't make a difference. But in regression, it makes a difference. Not in correlation, but in regression, it makes a difference, which is dependent, which is independent. So for this exercise, I ran the computer, and the regression equation is given in here. Price is 140.1 plus 15.89 times size. Now, if I translate this into our notation, so I'm going to actually, sorry, I want to show you everything. I'm going to write y hat is equal to, remember, b0 plus b1x. So that means y hat is equal to b sub 0 is the y-intercept, 140, plus slope is almost 16x. There you go. That's what that looks like. Now, the outputs by software usually use descriptive verbiage instead of x's and y's, because it just helps interpretation. Okay, that's why. Okay, so let me erase this now, and there you go, the equation. Now, something that I have in here, what does that mean? X is between 22 and 40. Well, if you look at the lowest the lowest home size here is 2,200 square feet, and the highest one in this data, so this is going to be the low, and this is going to be the high, right? This one. So I'm looking at the lowest and the highest. This is what we call the scope of our independent variable. In other words, what we're saying is that this regression model is only valid for the lowest size home, 2,200 square feet, all the way up to the highest, 40. That means 4,000 square feet home. So if there's a home that is, let's say you want to predict, you say, well, what if I have a 5,000 square feet home in that state? Well, this model is not going to be adequate. This is not going to be adequate because we don't have data on 5,000 square feet homes. So that's very important to note, by the way, is that we do not extrapolate in regression. Not this, what we're doing here. So remember, there's no extrapolation beyond the scope of your independent variable x. If you want to go beyond outside of the scope, then what we're doing is forecasting. Here, what we're doing is predicting. There's a difference between predicting and forecasting. Technically, they are different. Although you might want to say, well, when you forecast, aren't you predicting? You're right, in a way we are. We are predicting, but it's a different kind of prediction when we forecast. So anyway, that's why the scope of independent variable is important to note. Now, this is the analysis of variance. Every multiple regression analysis comes with an ANOVA table, an analysis of variance. Now, something that's interesting here, this ANOVA, it's got all these components of it, and let me just have your attention on the p-value here, right? This p-value. Anytime, remember, in an ANOVA, there's always going to be a p-value. So what are we testing here? When we talked about comparing several means, we used ANOVA, right? And in that work where we looked at comparing more than two means, we said the p-value does a test of hypothesis that the means are equal versus the alternative that at least one pair of means are different. So what is this p-value now testing? Well, this ANOVA, the ANOVA in regression, is testing the null hypothesis that you have the right model. In this case, you have the correct regression model, and more specifically, you have the correct linear regression model. The null hypothesis says that the model, let me write that for you. The null says that model is incorrect. In other words, the linear regression model is the wrong model for this exercise, for this problem. The alternative is complement of this, so that the alternative says, no, the model is indeed a good predictive model. I have the right model. Well, the p-value is very small here, right? Even if I use our generic alpha 0.5, it's going to be much less than 0.5, right? So in this case, we're going to reject the null hypothesis. That means the model is a correct model. Okay, so that's what this p-value is testing. Just want to point that out. Okay, and it comes in every regression model. So that's good. We have the right model for prediction. Now, this is, there you go. This is what this data looks like. Again, I did not use, so far I have not used Megastat, but Megastat gives you a similar output. We'll see it in a few moments. In fact, we'll see it for exactly this example. So there you have it. Price Y is equal to 140.1 plus 15.89x. X is the size. And for this specific one, I use Minitab, by the way. And don't worry about R squared and R and all this information here for now. Okay, so there you go. Here's your regression line, and these are the data points. Now, if you look at the regression line, we see this nice secular trend, right? It's going in that direction. Okay, so what that tells us is, as x increases, remember x is a size, as the size increases, so does the price. Which makes sense. You would expect that to happen, right? In that same state, if you will purchase a, let's say, 2,000 square feet home, you expect to pay less than if you bought a 4,000 square feet home, right? It's not twice as high, but notably higher. Okay, so that's what this is. And it made sense. We were expecting this, in other words. Now, let's take a look at our influential and outliers in this case. I believe, let me just go real quick. Yeah, that's coming up. But let me hold off on that one. So, let's say I want to predict the price or the value of a house that is 2,600 square feet. So, to do that, now remember, our values of x were 2-digit, not 4-digit. So for 2,600 square feet home, I have to put x 26. So that means x is 26. Don't put 2,600 in our regression equations. That would actually, if you put 2,600, remember the size is in 100 square feet. So add 2 more zeros in front of it. That's a home that's 260,000 square feet. And that's more of a warehouse, like an Amazon fulfillment center. Okay, it's not a house in that state. Now, so we're going to plug in 26 into equation, and there you go, we accomplish what we wanted to do. So the model predicts the price of the house is going to be $553,000, 2,600 square feet home. So if I look at now in my chart here, see, this is where 26 is, right? 2,600 square feet home. The actual value is just shy of 550,000. What we have predicted is 553,000. So this is what's being predicted right there. Okay. And there. Sorry about this one. Let me do this. There you go. This thing has a mind of its own. Okay, so this is what the predicted value is right up here. All of the points that are on the regression line, these are all, there you go, these are all predicted values at these levels of x. Okay, and of course, remember the scope of our data points here. we cannot predict anything outside of the scope. This model is good from here to about here. There you go. Oh, actually, I'm sorry. It's good all the way to 40, right? Because there's a data point at 40. You see that? So this is what the scope is. Okay. And we made our prediction. Now, what we are predicting, by the way, is keep that in mind. We're predicting the average selling price. So it is possible, for example, at 26, looks like I only have one home at that size, but note, it is possible to have more than one home at that same level. So which one am I predicting? Well, I'm predicting the average price. This is what we're predicting with this one. Okay. And now let's actually continue on. And let's take a look at the interpretation of the slope here. In a regression analysis, we don't really care about the interpretation of the y-intercept, especially like notice in exercise or in this example. This is the idea of y-intercept. Look at what I'm doing with the line. If I extend it, I'm actually going to come to a negative number. So, for example, if a house that is 0, that's when x is 0, right? When x is 0, I'm going to get a negative number, like negative 50. That means the price of a house that is 0 square feet means the house doesn't exist. It's worth negative $50,000. That's meaningless, right? So it's for that reason, a lot of times we do not interpret the y-intercept unless your data set is such that there is a data point x is 0 in it. Then you can interpret that. But with real data, most data do not have x is 0. So what's the interpretation of a slope? Now we always interpret the slope, always. Remember changing y over changing x, right? So more specifically for this exercise that we just did, this example, y is price, x is size. So we're looking at ratio of change in price to change in size. And the slope of the line was 15.89. And any number, 15.89, 1 million, 1,000, doesn't matter. Any number can be written as itself divided by 1. So when we try to interpret the slope, you always write the slope divided by 1, always divided by 1. Now remember, numerator is price in thousands, denominator size in 100 square feet. So what I've done here, next step, is to actually change 15.89 to 15,890 is what the actual number is. And 1 means 100 square feet. Right, each unit of x is 100 square feet. And then you reduce the fraction, you get 158.9. The units of the numerator are dollars, the denominator square feet. So this is going to be price per square feet in that state. So that's why the slope of a line is always meaningful. So that's actually good information for this exercise. So in that state, the price per square feet of the home is almost $160 per square feet. Which is much cheaper than San Diego, right? A lot of places in San Diego go for about $460 per square feet now. Okay, so there you have it. That was the interpretation. Now, continuing on with the idea of observational, influential observation and outliers. So based on what I see from a scatter plot here, looks like this point and this point. There are 2 points that are called influential observation. Notice you can have influential on the high or on the low end. And the reason why are they influential? Because they lie along on the high side and on the low side. They lie along the regression line and they are away from the rest. You see that? That's the, there you go. That's the bulk of your data. Then you have these two like an island onto itself. Okay, so those we're going to call in blue color. Those are our influential observations. And I have 2 potential outliers. Again, remember, outliers go in this direction. Vertical, away from the regression not alongside, but away from him in a vertical direction. So those are potential outliers. So what do we do with these, right? Well, you don't do anything with the influential observation. Unless, for example, now suppose something really strange happens here. Look what I'm going to do with this one. There, suppose I have an observation here. This is like a home that is 8,000 square feet. Well, that's kind of an unusual home in that neighborhood, right? So if we want, we can actually remove this one. And if my boss allows me to do that, I'm going to remove that extremely influential observation. Otherwise, we don't touch them. The other thing that we can do, by the way, in regression, there are different kind of regression analyses. We have this other other version of regression. It's called weighted regression, to where you can assign weights to observations. So we can actually change weights without having to delete data points. So we don't have to delete the independent variables. We can actually assign a lower weight to outliers and influential observations. But that's just to mention. So for now, we just want to identify them, and we did. Let's continue on. So that's all we want to do with regression. We're done with regression analysis here. Now, we're going to come in a few minutes to, okay, how do we actually establish the goodness of a regression equation? In other words, how do I determine whether the regression model is a good fit or adequate? Well, one way we do that is through the p-value here, right? Remember this? This tells me this is a good model. But again, as far as being a predictive model, I want to know, what's the predictive power of this model? Is it really good model, or is it a mediocre, so-so? What kind of model is this? Is this something that's that we can get excited about? So we're going to talk about that in a few minutes. But before we do, I want to talk about linear correlation, and then that would be a good segue into how we assess the goodness of a regression model. Okay, so the idea of a linear correlation, by the way, the keyword, there's only two words, linear correlation. Both of them, to me, are keywords. But one that's really important is the first word, linear. In linear correlation, we're looking at the strength of linear association. It means a straight line between two variables. Okay, so I will elaborate more on that in a few minutes, and I have actually examples of correlation and association between two variables that is not necessarily linear. So question is, how strong of, again I highlighted in yellow, how strong of linear association is there between x and y? Okay, now there are different measures of correlation, half a dozen at least. The one we're interested in is called Pearson product moment correlation coefficient. A lot of words, huh? And all of this. There you go. That's the kind of correlation we're looking at. The first word, Pearson. It's named after the founder of this, Professor Carl Pearson, early 1900, who came up with this formula, with this measure of correlation. The product moment, this has to do with the way the formula is constructed. The moments of a random variable actually have technical definition in mathematical statistics. And the product suggests there's multiplication, right? So those are just technical jargons. So we're just going to go with correlation coefficient. You can ignore the first three words. A lot of books don't talk about it. But to be complete, I mentioned it. So we just use correlation coefficient. Okay. So we use Pearson product moment correlation coefficient to quantify the strength of linear, again I want to emphasize linear here, okay, linear association between x and y. Now, in the population correlation, That means if you fit a regression line through hundreds of millions of data points. So for the population, we actually use Greek letter rho. That's again if you fit a line through hundreds of millions of data points. That's going to be a population correlation rho. But we're not going to work with population. We're going to change that into a sample correlation. For sample, we use letter R, lowercase r. So rho becomes R. Now, a few notes here about correlation. Okay, this is not in your book, but I will mention it just to be complete, because this is important when you do this. Our first note is that we actually have two types of correlation. We have what we call observational, and we have experimental correlation. Okay, so if our statistical study is observational study, then the correlation is also observational. But if we have an experimental design, then the correlation between two variables is going to be experimental correlation. Now, what's the upshot? What's the punchline, the high point? What's the point in general of this? What does this mean? This is very important. What's down here, right here? If you want to draw causation, you cannot do it in observational study. So the correlation between two variables, observational, is just that. It's merely an observation. It's like, wow, cool. That's all that is. But in experimental situation, we can actually draw causation between those two variables. Okay, we can say this is causing this. Okay, so for example, we can say that it is the price of a house that's causing the size of a house that's causing the price to go higher. And remember, we're looking at that in that same neighborhood, in that same maybe street. We're not talking about, let's say, zip code 92111 versus zip code 92076. We're not comparing those two zip codes. We're talking about the homes in that city block. So the size is causing the price to go up. That would be observational, and that would be experimental correlation between them. Okay. And my second note about this is that, remember, the key word here is linear. So we're looking at a linear correlation, linear association between them. So if there's another kind of association between two variables, linear isn't going to pick it up. So we don't use R in that case. Okay, this is reserved. R is reserved for linear. Note 3, if both x and y are random, then we have what we call a correlation model. Okay, and in a correlation model where both x and y are random, then x and y, I have it here, they're on equal footing since they're both random. So it doesn't really matter because we're not making a prediction. Keep that in mind. In correlation model, we do not make a prediction because both of them are random, and we just want to investigate the linear relationship between them. So we can switch your x and y, in other words. Put x in horizontal, y vertical, or put switch the variables. What used to be y, put it on x. What's the variable that's on x, put it on y. It doesn't matter. So in a correlational model, all we're interested is in correlation. So we're not gonna do prediction. That's why I say they're on equal footing since they're both random. Remember, for regression equation, however, for prediction, it makes a difference. We assume x is fixed and y is random. But in correlation model, they're both random. Again, this is not in your book, but I thought I mentioned it anyhow. Okay. So just to elaborate again, in a correlation model, we do not distinguish between variables. Okay. So it doesn't matter. You can do regression of x on y, y on x, and the correlation is the same. Okay, but the fitted lines will be different, of course. Okay. Now, and in a correlation model, again, x and y vary together, then we assume that each of the probability distributions follow a normal distribution. So x follows normal, y follows normal distribution for each pair, okay, at each level. And so the result's going to give us a joint probability distribution, and since we assume normality, the joint distribution of those two random variables is bivariate normal. This is again not in your book. What I'm talking in note 3 is not in your book, but I mention it because it is important, at least for you to know, even though you may not directly do this, but it's good information. Now, how do we interpret the correlation? Now, correlation, by the way, this Pearson product moment correlation coefficient, or correlation is always going to be between -1 and 1. Okay, mathematically, that's just how it works out. You never get a correlation that's 2. You never get a correlation that's -1.7. -1 is the lowest, 1 is a maximum. Now, here's how we quantify it. If you have a strong correlation, linear correlation between x, y, but negative, there you go. It's the correlation is negative, so that is labeled as a strong correlation, but negative between two variables. 0.8, anywhere from 0.6 to 0.8, you have what we call moderate. Between 0.8 and 1, you have a strong correlation. And remember, so the strong here is between 0.8 and 1, and it's also on the lower side, between -0.8 and -1. The difference has to do with the direction and the slope of a regression line, the direction of the two variables x and y, how they are oriented. I'll show you some charts in a moment. Okay. Now, a correlation of 0 here, that means there is no linear correlation. And notice in highlight yellow, I have everything is, I have made sure I have the word linear, linear, and linear here. So -1, perfect negative or inverse linear correlation. 1 would be perfect positive correlation, and 0 is no correlation. And these are some of the charts of what these look like. There you have it. So this is a correlation of 1. Look at the correlation of -1. In both cases, all the points fall on the straight line. The difference is the orientation of the line, right? This one is rising, this one is falling. That's what the difference is. And as the number gets smaller and smaller, notice how the points begin to fall apart. They disperse about the regression line. Okay, so that's what these correlation numbers are. That's how we quantify them. So you get a visual of what an R.4, for example, looks like. And of course, you have exact mirror images with negative correlations. And this is a correlation of almost 0. There is no linear correlation. Notice again, the author emphasizes linear, 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 linear in every one of these. That's very important. What most people don't realize, they just say, let's look at the correlation. Now, just to again show you the importance of linearity here with correlation. Here I made up this data. Okay, and I'll show you the equation of this and what I've done. But notice there is no straight line secular trend in this data. It starts low, rises, and then it falls back down as x increases. So what I did is I fit a line through this. Okay, right here, that's the fitted line. Okay, now if you look at the correlation coefficient, the software gave me for that is a -0.2. Remember, according to our correlation guide, a negative 0.2 is right in here under the poor, right? Anything between negative 0.2 and 0 is poor, getting close to really bad. Okay, so there's really poor linear correlation between them. Linear correlation, right? Now, and that's why if the scatter plot exhibits nonlinearity, we don't use R at all. This R squared, by the way, we talk about this in a few minutes. But this R squared, notice how it's near 0. That near 0 R squared kind of tells me the same. It's giving me the same information. We talk more about R squared in a few minutes now. So notice the fitted line is a poor fit, clearly. What if, because there's a clear bending here, right? You see that? Wouldn't that be nice if I knew how to fit a polynomial model through this? And this curve that bends in your algebra classes, remember this is the graph of a parabola. Okay. So if I know my algebra, let's say from before, this is a parabola, and if I know how to fit a polynomial model through this data, I can improve my predictions, right? And you'll see in a moment I've done that. Aha, check this out. Isn't that cool? This is much better fit than the linear that was this one, it was something like that. So much better fit. Remember these numbers, right? Remember these numbers here. Okay. Now, if you look at those numbers down here, again for polynomial, notice there is no R. So this doesn't even show up for a polynomial second degree model here, because I'm not doing a linear model. So the software doesn't even give me R because it's meaningless. But R squared kind of stays with us in multiple regression and simple regression. That R squared up here was almost 0, which is a bad thing. We'll talk more about R squared in a minute. But look at the improvement in the R squared here. Wow. From almost 0 to 0.97, this R squared maximum, by the way, is 1. 1 means every point. So this would be an R squared of 1. Check this out. So if I have a model like this, that would be R squared 1. It's going to look like that. If I have a data that follows this polynomial model, this would be R squared 1. If I have one that follows, let's say, a sine wave, there you go. That would be R squared 1. So you see what R squared 1 means? That means perfect fit for any kind of model. And we use R squared for linear, nonlinear. We use it for one independent variable, 1, 2, 3, 4. So for every kind of regression, every kind of regression analysis, R squared is meaningful. R is only meaningful for linear. Now, just to, look at the equation here, by the way. And this is the fitted parabola. The numbers, negative 17.5, 10.4x, negative 1.06x squared. That's what that is. Now, if you look at this negative 17, look at this one. 10.4, look at that. And negative 1.06, look at this, that's negative 1. The actual model that I created is this model. And the way I did this is I actually created a data, these data points that I created, 3, 4, 5, 6, and 7. These data points I created using this formula that I have down here, and I added some random normal disturbances, or some noise, call it. I added some noise to this data at these levels, and that's how I got these points to plot. And then I told Minitab, okay, can you fit a line through this? Or not a line, I'm sorry. Can you fit a curve through this? And it did. And notice though how the how the estimated value of those parameters are again close to the actual model. Now in real life, we don't know this, right? You don't know who made up these numbers or where data came from. You just have a bunch of data points and you fit the curves through them. So again, I just want to show you the importance of R is only being used for linear regression, simple linear regression. Okay, now let's move on to coefficient of determination. So here's a couple of questions I have. Question 1. How reliable or adequate effective is the regression line or regression model in general for making predictions? Is this line any good? And how are we going to measure the effectiveness of a regression model if we were to do this? Okay, based on what metrics? The answer. Well, this is going towards coefficient of determination. Okay, but the answer on as far as how we're going to do this. So we're answering the second question, this one. Okay. So to answer this second question, we say, well, let's look at total variation in dependent variable y and see what percentage of this variation is due to presence of x. That would make sense. So for example, let's say I'm looking at total variation in price of homes in my neighborhood, and I'm looking at what percentage of these total variation in prices is explained for by size of individual homes. So that's going to be the premise for it. And here I have actually the idea of how we're going to do this explain variation. So if you look at, let's go back here. So again, I have a case where I have actual number. Up here, this dot, this is the actual y, this is predicted. And this is the average. The average, let's say, is 10. The average response variable, y bar, is 10. So if I look at the difference here between predicted value and average is 1. Difference between observed value and average is 5. Okay, so we can actually break this. So 5 minus 10 is 5 units from this point up here, from the solid circle to the average is 5 units. From the square box, which is on the regression, to the average is only 1 unit. So this 5 unit distance from top to the average can be broken into distance from there to the square, from square to the line. That part is 4 units right in here, and this part is 1 unit. Now, if I take the ratio of 1, which is this portion, 1 to the total deviation, that gives me 0.2. Okay, now, as far as the regression model. So notice this part, this point is fixed, right? That's observed, that's 15. But let's say my regression line now is such that it goes up closer to the observed value, and that's what I have here. I made it get closer to observed value. Y bar is the same, fixed number 10. Now let's look at this. Notice the closer the box, this predicted value to the observed value is, the better, right? So here, up here, 11 is 4 units away from 15, not good. Here I made the point closer, so that's only 2 units away from the observed value, and that's a good thing. So this distance between the red box, the predicted value, and y bar, they tag that as explained variation due to regression, and the difference between observed and predicted value is what they call unexplained. So how come there's 2 units difference between them? I don't know. That's unexplained. But this portion of the distance from here to here is called explained variation, right? So again, that distance of 5 units now is broken into unexplained is 2, explained is 3. Compare that to up here. Up here, the unexplained is 4, explained is 1. So if I take the ratio of now explained 3 to total variation at that point is 5. I get a ratio of 0.6. 0.6 is higher than 0.2, so that's a better number. The higher, the better here. And what the higher would indicate is that the predicted value is closer to observed value. So again, that's a good thing visually. So, and these numbers are actually percentages. So we're going to call y1 minus y hat 1 explained variation. That's this one. Okay. That's y1 minus y hat 1. This part, that's actually going to be unexplained variation. And the difference between y hat bar and y bar is going to be explained. Let me actually fix this part up. Okay, so then when I went ahead and fixed it. So again, this part is unexplained. That's what this is. That's y1 minus y hat. The difference between observed and predicted is unexplained, but the difference between predicted and the average of the y values is explained variation. Okay, that looks good. Now, what I have here, we'll see a more elaborate drawing here for it. So what this figure is doing is actually looking at the deviation of an observed value up here from the average, and it partitions it into two parts. Unexplained is right here, and this is explained variation, just like I have up here. Unexplained up there, explained, and there you go. So this is pretty much what I did, only drawn a little better. Not little, much better. So now imagine we do this for every data point, and keep in mind, the closer the predicted to observed value is, the closer it is, the smaller the unexplained portion is, the higher the explained. And remember the ratio, we're going to look at the ratio of explained portion to total. The higher the better. And that's what's coming up. Now, in here they talk about total sum of squares here. So if we look at these again, what's in here, if you look at these, you square this, add them up for every data point, you get what's down here. So the total sum of squares, that's total variation in y values, yi minus y bar, that's this distance. That would be from here to here. This distance. That's what this is. And they square it. And if you add these up, sigma means do this for every data point. Okay, so that's the total. And then you're going to break that into regression. So this part of it is called a regression, and this part of it is just unexplained. This is the error. Okay, this part of it is the error. And symbolically, that's what those are. Okay. Now, and then from that we get our what's called regression identity. The regression identity says sum of squared total equals sum of squared regression plus error. Symbolically, that's what that is, but don't worry about this one. We use Megastat. And anyway, remember the whole question was how we're going to determine, what's going to determine the adequacy of the model. How do we determine if the model is good? So goodness here is based on the ratio of explained variation to total variation. And the explained variation is explained by regression, and this is total variation, and that's what this ratio is. So all of that is just to formulate a ratio that makes sense, a meaningful ratio. Now that ratio is called coefficient of determination. So what is this? Notice this R squared, by the way. R was linear correlation coefficient for simple linear regression. R squared is actually, in fact, when you square the R. Now, what's the interpretation? This is important right there. So what is coefficient of determination? It is the percentage. Proportion means percentage. It's the percentage of variation in observed values of response variable, that's your y, explained by the regression, okay, or is due to independent variable x. Okay, so R squared is a percentage. Okay, now because sum of square SSR, at most SSR can be is equal to SST. Okay, at that point there is no error. Means every point lies on the regression line to where explained variations are exactly the same as total variation. So because of this inequality, R squared always lies between 0 and 1. Now, square root of R squared gives you the correlation coefficient. That's what that is. And R squared itself, remember R was correlation coefficient. Where you square correlation coefficient, you get coefficient of determination. Okay. And there you go. This would be an R squared of 1 in my graph. Notice observed values are circles and predicted values are in squares. Exactly on the regression line, everything lies on the line. So there you go. And if this is, let's say, let me draw a line, hypothetical, let's say this is y bar. So the difference between observed and y bar is exactly the same as predicted and y bar. So that's what's gonna happen here. Okay, oops, I didn't want to do that again. Let me put that line back on there. Okay, I put the line back on there. So anyway, that's what R squared 1 means. So remember, explained variations show how much of the deviation from the mean is reduced when the regression line is fitted to the data points. That's what we mean by explained variation. So for our housing example we saw, the regression output gives us, this is portion of regression output. It does give us, right in here, you see that, RSQ, it gives us R squared. All right. Now also it gives us adjusted R squared. That's what ADJ is, adjusted. In the case of simple linear regression, don't worry about this number at all. Okay, this adjusted R squared makes a difference in multiple regression when we have more than one predictor. So for example, that's if you want to determine or predict the price of a house based on the size of the house. Let's say the number of bedrooms, bathrooms, the lot size, the age of the house, the amenities, and so on and so forth. So then R squared adjusted makes sense. But there you go. Now here's RSQ, R squared. Call it 70%. That's what that is. In this part, we will talk about this later in a few minutes. Okay? But for now, from this portion of the output, this is all we're interested about. So our R squared is about 70% here. That means 70%, and I have the interpretation here. It's almost 70% of total variations in home prices are explained by, remember, these are explained variation, right? Explained variations, that's what those are. So 70% of total variation in home prices are explained by the size of the house. That's good information. So as far as like R squared values, let me see if I draw my line here. This is 0, maximum R squared is 1. So anything let's say about 0.8 R squared, 0.8 to 1, the model is a good model. Anything between 0.6, 0.8 is what we call adequate model. That's adequate. And you kind of see how things are getting worse again near 0. 0 is worst model. You don't have a good model. So we go from good to adequate to poor and so on. Okay, so anything between 0.3 to 0.6, it's a poor model. And R squared between 0 and 0.3, call it very poor. not good at all. Okay, so that's our, let's say, yardstick for R squared. And I want to show you by hand. If I want to do by hand, this is how you do it by hand. But again, you don't have to do anything by hand here. We get everything here from Megastat. Now, there are 4 assumptions associated with the linear regression model. I'd like to mention these. 1, linearity between x and y. The second one is what we call homocydasticity of errors. Okay, homocydasticity of error means error terms are not homogeneous. I'll show you an example of homocydasticity. Okay. Independence of observations. Okay, that makes sense. And normality. For a fixed value of x, y is normally distributed. Remember, we use a fixed model regression. Means x is fixed, y is random. And here's what a violation of second, the homocydasticity, means being the same. Homogeneous, think of it as homogeneous. Homocydasticity of errors. See this funneling effect? This is a case where the error terms are heteroscedastic. So our assumption is that we have homocydasticity. Okay, and there we have that. And we can use the regression diagnostics to do these things and stuff. The regression analysis is a really drawn out procedure. Okay, it's not one thing you do, here's the equation, I'm done. It's actually a group of procedures that we follow in order to determine the predictive power of a model and then different aspects. So there you go. What am I doing here? This is assumption 4, normality. What do we mean by assumption normality? For any fixed value of x, y is normally distributed. What does that mean? This is what it means. Okay, so here I have actually 3 levels, x1, x2, and this is, let's say, x3. Okay, at every level the distribution is normal of y. So the y values, these are the y values. Okay, so we expect y values to be random. So at the level of x1, let's say I may see a y here, or I may see a y here. I may see a y value here. See, those are these are random. But x is not going to change. See, same level of x. At x2, this is what I might see, this is what I might see. At x3, I may see this, and I may see that. So you can kind of see a scatter plot with blue circles now. Okay, so that's what that is. Now, the normal distribution that you see, all these normal distributions, every one of these has different center. See the center of this distribution? Look at the center of this one, center of this one. The centers are allowed to change. They change according to the regression line. But every one of them has the same standard deviation. Okay, so that would be sigma, and for this one, that 2 is sigma. You see that? So that's what that is. And oops, sorry, let me put that back on there. Okay, I put that line back on there. So anyway, that's what the assumption is. That's the assumption of normality at every level. And again, the final note here is that the center of every normal distribution here is allowed to be different, and is determined by the regression model. That's why when I mentioned what are we predicting, we are predicting the center of these distributions, the mean or the average. That's given by the regression line. So that's the assumption. Now, we are near the end here. The other thing, information that's in the regression output is this piece right in here. Okay, what is this? The letter S here stands for standard error of estimate. Okay, and that number is 59.62 for our housing example. the home prices example. So what does this standard error estimate is? That's actually an estimate of that. It's the estimate of the common standard deviation. Okay, so that's what that is. And the way I interpret this is that is your give or take. So in other words, any value that you predict for any price of a home you predict for a given size of a house, every one of those predictions at every level could be off by as much as almost $60,000, a fixed amount. So when you predict the price of a house that's 2,000 square feet for this data, you could be off by 60,000. Price of a 3,000 square feet could be off by 60,000. What if it's 3,500 square feet? The prediction could be off by 60,000. That's what the error of prediction at every level is. Okay, so there you go. We're done with this chapter. And now let me actually go show you an output from Megastat. So here's the output from Megastat. Okay. And I'll show you this scatter diagram in a minute. So the things that are familiar, we've talked about almost every part of this now. So this is the R squared, coefficient of determination. This is the correlation. Now, one thing that's important, by the way, folks, both of these are decimals. R is not a percent. R is not a percentage. So 0.829 doesn't mean 82.9%. It's just a number between -1 and 1, okay? But the number above R squared is a percentage, so that's 68.7%. That one is okay, but not R. Okay, so please note that also, that R is not a percentage. And so there you go. Both of those numbers we saw earlier in another output from the other software I used from Minitab. Dependent variable is Y. Price in thousands. Here's the ANOVA table. Don't worry about all of these stuff here. And this is your p-value that we saw. 0.0058. Remember this ANOVA. What are we testing here? We're testing the hypothesis that you have incorrect model or not. The null says you have incorrect model. We're going to reject that null. Our p-value is small, meaning we have the correct predictive model. Now, this number also, I'll write this in here. This one, MS, by the way, that stands for mean square. Mean square. SS stands for sum of squares. Now, this number, MS residual, is actually the same as error. So some people label this number in highlight MSE, mean squared error. This mean squared error, something is interesting happens. If you take the square root of this number, you get what's in here. Okay, so you can try it if you have a calculator. Take the square root of 3554.6343. You're going to get 59.621. Remember the standard error, the common deviation for those normal distributions. Put a hat on it. This is an estimate of those common deviations in the population. So if I take a square root of this large number and get this other number, that's what the variance was. If you take the square root of variance, don't you get standard deviation? So this number 3554 is an estimate of the variance, but we use standard errors rather than variances. Okay, just want to point that out also. And let me erase these. We don't need these now. Okay, going further south. Now this is only in from Megastat. So in here it says regression outputs now, in the regression outputs. So it does list the variables. Remember, there's only one variable we have here, and that is x, right? That's our only variable is x. It's a simple linear regression. So x is the size in 100 square feet. The coefficients are the numbers that multiply by these. Coefficient on x is 15.89. Our y-intercept is 140. Okay, so that's what those are. Don't worry about these. Don't worry about these. But next to that, we have these p-values, right? Now, the p-values, don't worry about this one. We don't really interpret that. But this other p-value, 0058, which is no coincidence, is exactly the same as that. See, those are the same. In a case of simple linear regression, that will always be the case. In multiple regression, those will change. Okay. So, this actually, what's this p-value testing? Here, this 0058 test is this. The null hypothesis says slope is 0. Okay, and 0058 is very small. You're going to reject the null. So the alternative here, what does that say? Slope is different from 0. And remember, slope 0, when we first started this chapter with a review of algebra, slope 0 means you have flat line, right? A flat line, and let me do up here. When we have a flat line, that means your data is like that. It means there is no trend in your data, right? So that's interesting. These two hypotheses are testing the same phenomena. If I have a ball of numbers, a slope 0 means there is no linear association between x and y. That means I have the wrong model. And that's what exactly the ANOVA is testing. Okay. So that's what this one is. In your book, they do test the slope. And that's what this is. Okay. Okay. Now, going further south. Okay, let's go down. Finally, this is the last part. I didn't talk about this, but it comes in the output. Might as well talk about it. So here's the predicted value of y when x is 26. I did it up here. Let me go up. Remember, we made a prediction right up here. And there is our prediction. Right up here. Was it up here? Yes, we did. This is our predicted value. Remember this one? $553,000. You can actually get Megastat to make that prediction. $553,000, and that's what Megastat Outputs gonna give us. Sorry, I scrolled fast, I know, but I just want to get to the bottom of this output. There's your $553,000 predicted value at that level of x. And this is interesting, 95% lower confidence interval, 95% upper confidence interval. So what we're saying here is the predicted value. The average predicted value for the 2,600 square foot home is anywhere between $492.6 and $614,000. Okay, that's what these numbers tell us. Our predicted value is, on average, is somewhere between these two, 493,000 to 614,000. And this one is what we call prediction intervals. Now, prediction interval is interesting, actually. What's the difference between confidence interval and prediction interval? Remember, the confidence interval is constructed about the mean. So with this one, we're looking at mean selling price. That means the average selling price of a 2,600 square feet home. The keyword is average, mean. The 95% prediction interval, and notice these are different. Lower is 400 almost. Upper is 707. Wider range than the confidence interval from 493 to 614. This is a wider interval. Okay, so what is this one telling me then? The prediction interval is used for this. Suppose I'm going to go to that estate, Phoenix, Arizona. I'm going to look at a house, a single house that I really like. And that is a 2,600 square foot home. That happens, that the one I'm looking at. The size that we are predicting. It's got to be 2,600. So I'm looking at a single home. We're not looking at the average of several 2,600 square feet home. I'm looking at this one home, this one house, 2,600 square feet. And I'm asking my, let's say, real estate agent who's with me at that moment. I'm going to ask him or her, what is the price of this house? I don't care about average house. I like this house. What do you think the price of this single house is? And he or she's going to tell me that price is anywhere between $400,000 for that house to $707,000. See that? So prediction interval is constructed for a single observation, whereas confidence interval is constructed for the average selling price. Okay, so that's the key difference between them. Megastat gives you that. And the leverage here, don't worry about that one on the leverage. Okay, and there you go. With that, we can go now to Megastat. Oh, I was going to show you the scatter plot, right? Okay, and here's the scatter plot. Let me scroll down. There it is. Pretty much like the one I had using Minitab, right? So here again, this is our influential. There are two influential observations and two potential outliers in this data. And again, everything looks the same as before, your regression equation. So Megastat gives you right in here, gives you the regression equation as well as the R squared. You see that? And that's what that is. Horizontal axis is size, vertical axis is the price. Okay, and there you go. Now let's go together to Megastat and let's get exactly this output from Megastat, and then that will complete our lecture. So let me pause and go to Megastat. Okay, so now I am in Excel and I have my add-ins. So I went ahead and typed the data in, so you don't have to waste time watching me. Or I don't have to waste your time watching me, not you don't waste time. I don't have to waste your time watching me input these. So there you go. This is exactly what the raw data looks like. So I'm going to go to add-ins and we go to Megastat. Now if I want to get the scatter plot, first we're going to go correlation regression. And there you go, scatter plot. Click on scatter plot. Input range, horizontal axis. Include the label. Left click once and drag. Once it's outlined, then we're going to hit enter on this. Okay, I'm going to hit enter. Sorry, let me see. There you go. Enter. And then I'm going to go vertical axis. Include the label. Drag all the way. Enter. Now the chart title, I didn't give it a title. You can give it a title that you like. Let's say I'm going to go scatter plot of housing prices. There you go. Now here, if you uncheck it, it will not plot the linear regression. We really do want to do that, so I'm going to check that. Force zero intercept, we don't want to check that. If you do then the regression line will go through 0, 0. I guess some of the, let's say, physical sciences may want to do that, where when x is 0, y will be 0. So we're going to let the intercept actually free float. We're not going to force it go anywhere. Display with markers and lines only. So I'm just going to keep it markers. That's it. Look how simple that is. But that's just for a scatter plot. Hit OK. And there you go. So that's what I had. There's your scatter plot. Just like the way I had it before. I'm going to go to sheet 1 again. So, or you don't have to actually. So this is my output, right? So I'm going to go to, let's run the regression now. I'm going to go add-ins, Megastat, correlation regression. And for this one, we go regression. You do not need to use correlation matrix. We use correlation matrix in multiple regression. We don't use it in single linear regression. Simple linear regression, where I have a single x. That's for if you have x1, x2, x3, where you can look at correlation among independent variables. So we're just going to go regression analysis. Click, left click. Now, x, independent variable, input range for x. I'm going to go to sheet 1 and input range. Oh, I'm sorry, that was for x, right? No biggie. X, enter. Y, which is your dependent variable, and here's my y. And remember, we want to predict the price, the average price of a 2,600 square feet home. So here it says no predictions right now. I'm going to check. I'm going to type in predictor values of a 2,600 square feet home. Now, if you want to do more than one, you could. I believe you put comma, and let's do a 3,000 square feet home also. Why not? Now, down here, I'm just going to keep that check, test for intercept. Remember, that's the null hypothesis. Intercept is 0. Everything else, leave it unchecked. The things that are on residuals on the right side, these are our diagnostic tools for regression assumption. Okay? Don't worry about those. And that's it. Hit OK. Oh, let me see what happened as occurred regression calculations. I'm not sure what's wrong. It gave me an error, but it calculated anyway. So anyway, whatever that was. So, and you can see exactly the things that we had. Now, notice I did not highlight these. So the software, when the p-value is less than 0.5, the software will mark these with different colors. Less than 0.1, it highlights it in yellow. If it's between 0.1 and 0.5, it uses like another color, but it's not yellow, but it's kind of like orangish color, light orange color, kind of. But anyway, here's r squared. So that number 0.687, remember, this is the coefficient of determination. That's what that is. Okay. R is 0.829. This would be the correlation coefficient, right? And the standard error, 59,000. Now remember, this is the error of your prediction at every level. And everything else we just went through. So these are the, see this prediction. It's going to be intercept 140 plus this number times x. This is your prediction line. And oh, here's our predictions. Remember, in my OneNote, I had predicted x26. In here, I added the 30 also. So that's how you get multiple predictions. The average price of a 2,600 square foot home, 553,000. 30 square foot becomes $617,000. And then with these. Okay. And there you have it. So with this, we are done with this chapter, and hopefully you'll be able to now do your homework problem. And please do read the book and take look at the author's take on this. And with that, we are done with chapter 13.